Today, we're going to play detective. We've got two chemical mysteries on our hands that on the surface seem like they have nothing to do with each other. First, what's the deal with certain compounds having these incredibly vibrant colors? And second, why is a water molecule, the stuff of life, bent into that classic V shape? Turns out, the answer to both is the same. It's a single, powerful concept, a kind of secret universal language that all molecules speak, the language of symmetry. So let's start with puzzle number one, color. You've seen it, right? That deep, brilliant blue of copper sulfate or the crazy purple of potassium permanganate. Well, those colors are no accident. It all comes down to how these compounds absorb light, and to understand why they do that, we need our first clue. So, our investigation kicks off with a model called crystal field theory. Now, this was really the first big attempt to explain what's going on with these colorful compounds. And look, it's not perfect, but you'd be surprised how close it gets us to the truth. The idea behind crystal field theory is, honestly, super simple. It basically ignores all the messy details of chemical bonds and just pretends that the metal atom in the center and all the molecules around it, we call those ligands, are just little points of charge. Just imagine the ligands are like tiny negative magnets, and they're pushing away the electrons in the metal's outer orbitals. That's it. It's a totally electrostatic model. Okay, so this pushing and pulling has a really cool side effect. A metal has these 5d orbitals that normally all have the exact same energy, but when the ligands come in, they get split. Some of the orbitals, the ones pointing right at the pushy ligands, get shoved up to a higher energy. The others, which are pointing in between the ligands, actually drop down to a lower energy. And this energy gap that's created, it's the perfect size for a photon of light to come in, get absorbed, and kick an electron across. The color we see is just all the light that's left over. And what's wild is that for such a simple idea, crystal field theory works shockingly well. I mean, it's great for predicting things like magnetism, color, even the structure of these compounds. But here's the plot twist. The main idea it's built on, that these bonds are just simple electrostatic forces, is totally wrong. We know for a fact that bonds involve sharing electrons. So yeah, CFT is a handy shortcut, but it's a model built on a shaky foundation. We're going to need something better. And that brings us to the next stage of our investigation. To get a clearer, more accurate picture, we need to level up to a more sophisticated model. It's called ligand field theory, and this one gets us way closer to what's really happening. Okay, so ligand field theory is actually part of a much bigger, more fundamental idea called molecular orbital theory, and this changes the game completely. Instead of orbitals just being pushed around by charges, LFT says that the atomic orbitals from the metal and the ligands actually merge. They overlap, and they form brand new orbitals that belong to the entire molecule. The best way to think about this is like a corporate merger. Crystal field theory was like two companies just setting up across the street from each other and repelling one another. But in ligand field theory, the two companies actually merge. The old departments, the atomic orbitals, they're gone. And in their place, you have new, fully integrated departments, the molecular orbitals that are made from the old ones. It's a much, much better picture of how chemical bonds actually work. But this brings up a really important question, right? In that corporate merger, you can't just mash the accounting department and the creative department together and hope for the best. They have to be compatible. So, how does a molecule know which atomic orbitals are allowed to combine? What are the rules for this merger? Well, it turns out there's a fundamental rulebook written into the laws of nature. The rules of engagement for how these orbitals can merge are all governed by one single, elegant principle. And that principle is symmetry. It is the universal language that determines everything. If two orbitals have the right kind of symmetry, if they match, they can combine. If they don't, they can't. It's really that simple and that profound. Okay, whoa, I know what you're thinking. This looks intense. This is called a character table, and it's basically the dictionary for that language of symmetry. But seriously, do not panic. Ignore all the numbers. For what we're doing, we only need to care about those labels over in the far left column. A1, A2, B1, and B2. Just think of them as simple name tags. These labels are called Mulliken symbols, and you can just think of them as compatibility tags. It's a code that describes how an orbital behaves if you were to, say, rotate or flip the molecule it's in. And here's the golden rule. Only orbitals that have the exact same Mulliken symbol, the same compatibility tag, are allowed to interact to form a bond. Same tag, they can mix. Different tag, nope, not allowed. So how does an orbital get its tag?
Well, we basically just see how it behaves when we mess with the molecule. For something like water, an s orbital is just a perfect sphere. It doesn't matter how you rotate it, it looks the same, so it gets the most symmetric tag, A1. The pz orbital also happens to line up in a way that gives it an A1 tag too. But the px and py orbitals, they change when you rotate them, so they get their own different tags, B1 and B2.
And all of this brings us to the most important point of this whole explainer, summed up perfectly right here. When bonds are formed, atomic orbitals combine according to their symmetry. This isn't just a suggestion, it's a fundamental law of chemistry. It's how molecules are built, period. All right, we've got all our tools. We know that orbitals have to match their symmetry tags to combine, and we know how to find those tags. So now, let's use all this to finally solve our second mystery. It is time for the million-dollar question. We all draw water with that classic V shape. We know its bond angle is about 104.5 degrees. But why? Why isn't it just a straight line? I mean, that seems like it would be simpler. Well, as you've probably guessed by now, it has everything to do with symmetry. And here's a little hint for you. You probably don't want to pour it on your water, but see that A1 label? That's the exact same kind of compatibility tag we've been talking about, and it is the absolute key to understanding why water looks the way it does. Okay, here's how we build it step by step. It's actually pretty straightforward. Step 1, find the symmetry labels for all the orbitals on our central oxygen atom. We already did that. We got A1, B1, and B2. Step 2, we do the same for the 2 hydrogen atoms, but we treat them as a single group. Turns out their orbital combinations have A1 and B2 symmetry. And finally, step 3, we just play matchmaker. And look at that, it's a perfect match. The oxygen's A1 orbital can mix with the hydrogen's A1 combo, and the oxygen's B2 orbital can mix with the hydrogen's B2 combo. Those are the symmetry-allowed handshakes that will form the bonds in water. But notice the oxygen's B1 orbital? It doesn't have a match on the hydrogen side, so it's left out. It just becomes a non-bonding orbital. And here it is, the big finale. When these specific orbitals mix together in their symmetry-allowed ways, the new molecular orbitals that are formed find their happiest, lowest, most stable energy state in a bent shape. If the molecule were linear, it would actually be a less stable arrangement. The bent shape isn't some random accident. It's a direct result of the molecule finding the path of least resistance, a path that is strictly paved by the rules of symmetry. So we did it. We solved both of our mysteries, all with one single powerful idea. Symmetry explains the energy gaps that give chemicals their color, and it dictates the exact orbital handshakes that force water into its iconic bent shape. Which kind of leaves you with one last big thought, doesn't it? If this one principle can explain so much, what other secrets of the universe is it just waiting to unlock?